Okay, so we'll do the double integral in polar coordinate. Okay, first, uh, let me remind you of this, what we call the rectangular. Well, this is rectangular in Cartesian, means the uh, x is the bounded by two constants. C is y is bounded by two constants also. So you have this one, A, B, C, and D. So this is what we call the rectangular in Cartesian. Okay. However, when we have a rectangle in polar coordinate, that means the R is bounded by two constants, okay, from below and from above. And theta is also bounded by two angles, say alpha and beta. This is what we have. Okay, so the shape of the rectangle, the so-called rectangle, here is quite different. Okay, so that's the basic shape in polar coordinates. This is the rectangle. So when you do the partition in this rectangle, this is how you partition the R. So this is delta R. Okay, and so this is delta theta. Okay, so what's a little bit weird here, because this is radial, delta theta may be the same thing here, but this is, looks small. But delta theta here must be quite big. And farther away from zero, you see this delta theta is big. Okay, so same delta theta here. So depending on the distance from the origin, the farther away from zero, and delta theta becomes bigger. Okay? So that's delta theta is depend on the R, depend on the distance from zero. That is R. All right. So in fact, uh, when we compute the R here, it is not only okay. So this is not only uh, delta theta times delta R, but also you have this one. So this is our, sorry, I should say A, delta A. Okay. So this should be the area later on. Okay, if you have this, just this is the A. Okay, so if you have a double integral in terms of Cartesian coordinate, you have in the integrand is f with variable x and y. Okay, and when you convert uh, to polar, you substitute r bar by r cosine, x y by r sine, and dA is replaced by not dx dy, but not only dr d theta, but here you have extra r. Okay, so there's no difference in terms of the region. Must be r, same r, only the expressions different. This is the one that I mentioned earlier. All right, let's do this one. Let me just summarize in a couple of sentences here. polar coordinate. So in so the idea here is to partitions. When you do partition, okay, yeah, partition, okay, and take a sample. This is length, sorry, delta R, delta R. Here's the length of this is R, sorry, R theta. Okay, so delta A is delta R times R delta theta. So we use the for just R there. Okay, so if you have this integral over region R, okay, so in polar coordinates, it looks like it's still R, but the expressions now is R cosine, R sine, and dA is R d theta. Okay. So example. Let's compute one. Let's yeah. I think this is the one from the beginning. Let's make it more complicated. More complicated. This is the R. Okay. So this is x squared plus y squared equals 4. And this one. All right. So let's do this one here. Compute this one. So this is D. R. Say R. Okay. One first. Let's do the boundary first. So how we should move if a x directions is going from left to right. Right? You say y is going from bottom going up, so from below going to above. And the thing here, what we do with the within polar, this is in Cartesians. What about in polar? In polar, R is going from 0 going outside. Okay, because this always from 0 going outside radially. R is radial. And theta is sweep angle. Okay, so this is in polar. All right, so if we have this one, okay, so what about from not really from zero, from inside outside? Okay, radially. All right, so let's see the R now. R is from inside to outside. Let's see here, really going radially. So start from here, going to outside. From here, outside. There. Okay. Now this one has equations R equals 1. Here you have R equals 2. Okay. So in this case, R from 1 to 2. Okay. And what about theta? Well, theta is sweep. Sweep from 0 to there. So that's the theta direction. So from 0 to 0. R. Okay. So the region now can be expressed simply as a this is a r theta, r between 1 and 2, theta from 0 to 5. So this is our r. Okay. So this is something that is complicated if you try to express in terms of Cartesian, because you have to divide the r by two simple regions, two simple domains. Okay. But using polar, this is easy. Okay. So when we do this one, okay, so let's see. At the end, you have this one. So r from 1 to 2, theta from 0 to pi over 2. Okay, so this is x squared plus y squared is that's r squared. Okay, we have r squared, and dA is r, dr d theta, right? Okay, so observe this one. Okay, you see r here is the 1/2 of the derivative of r squared. So using substitutions, you can see this is time at loop. So 1/2 e to the r squared. Okay, r equals 1, r equals 2. There you go. This is data. Okay, so everything in terms of, there's no dependence on theta. So just multiply by theta. So pi over 2. And here we just have, see, 1/2, another 1/2, so 1/4. Oh, yes. Without simplification, just pi over 2 from here. This is 1/2. And this one, e to the 4. And this is okay, so Questions so far? All right. Another example is this one. All right, so this rather complicated expression. Um, say this. Sorry. Make it equal. There we go. So this is a improper integral with a with this minus. Sorry. Okay. So there's no way to compute this integral using the technique that we know so far because this e to the has no antiderivative. Okay. So what we can do for this with this problem. All right. So let's say let's say this one. Let's do this trick. Let I equal this integral. Okay. So what is I squared? I squared is this one still the same, right? Because it's the a variable is dumb anyway, so dummy variable, right? So whether you're using X or Y, that's the make no difference. Okay. However, if you put them together, okay, if you use different uh, different letter, then you get times e to the y. Okay. And then this one is actually there. Okay, so this integral in double integral in polar coordinate. Okay, so the area here is the whole thing. Okay, so in term of in term of polar, r it goes from 0 to infinity, theta from 0 to 5. Okay, so in polar, this integral should be 2 pi, okay? Infinity, this is r. And this one becomes e to the negative r, okay? And dA is just R, dR, d theta. That is something that we have computed earlier. Okay, so let's do some equations. That is the limit of t infinity to b. Okay, so this is okay. Then you get this is 1/2 e to the 8 1 squared. Okay, so this limit. Uh, 1/2 e to the negative b squared with 0. This is 1. Okay, and when you put b to infinity, this goes to infinity, but negative, let's go to 0. Oh, sorry, I should say there's negative sign here. I think in this example also made, oh no, that's correct, because that's positive. This is negative exponent to 0. So negative 1/2. So this is just 1/2. Use this negative 1. Okay. So continuing with this, equals to 0 to pi times, we complete this one, the theta, which is pi. Okay. So at the end, we do this one. Oh, that is pi squared, right? So at the end, we can pi, which is for this. Yeah. All right. So that's the magic of this this integral. Well, you'll find this later on in statistics. You see this one. This is the basis for the uh, normal distributions. So you got to be able to compute this shape in statistics, right? Okay, so that's questions. Order, where is the folder? To 16, for example. Okay, to 16. Then is that thing. Um, say part A. This is a rectangle because you're going from inside to outside radially. You see that's going, yeah, going there. Okay, so this radial is coming from 2 to 4. Right? Oh no, sorry. It's this. Oh, theta 5. Sorry. So R will come from 2, 5. Okay. And theta, the theta is angle, so it sweeps there. Okay. So from this is negative pi over 2 to, let's see, what's the angle for this? So theta here, tangent theta is y. Okay. So theta is R10 3/4 there. Okay. So that's the area. So well, R between 2 and 5, and theta from 2 10 and first 3/4. That's all. Okay. Questions? All right. So let's again. Mr. B. Okay. So this is the okay. Uh, so now the question is, let's see here. So the radial start from here and up there. Same thing. So this is R equals 1. We have to find the equation for this vertical line. From 1 till whatever here. Okay, but for here, you see, it starts from R equals 1, but end up with something here. So this horizontal line. So we need to find that is the threshold. Okay. So from theta from so this one is, let's see. So from and theta equals y over x, so 2, 2. Okay, so what's the angle for theta? Gives you the square root of 3. So we just say yeah. So it's let's see, 60 degrees, I think. Okay, so it's because 10 pi over 3, this is 1/2, this is no. So 10 over 3. All right, so this gives you, all right, so this equation is now vertical lines. Vertical line is y equals something. Equals 2. All right, so, but y is r sine. Okay, so here r 2 over sine theta. Okay, so that's the vertical line. In horizontal lines, x equals okay. So if you replace this x, so this r cosine theta is just 2. So r here is 1 over this. Okay, so this would be, all right, so first part, so from theta from 0 to pi over 3 here, and r is between to this line, vertical line, and second part is theta from pi over 3 to, it's read from here from 2, this one, to pi over 2. R is between, from 1, sorry, this is R from 1 until here. Okay, so this is the expression for this area. Okay, questions? All right, if not, then let's go to our example. Right, 19. Let's see, 19. Okay, so this one. Okay, find the solid, volume of the solid above the xy plane, bounded by these two surfaces. Okay, okay, so this is uh, an ellipsoid, and this is a cylinder. Okay, let me just recall. Okay, so let's see what this cylinder and this ellipsoid looks like. So we divide this by, let's see, divide by 18. Okay, so it's 2 over 18, so 2 over 9, right? Plus 9. Okay, I would say this one. Square root of that. Square root of 2. Okay. Okay. So this gives you the x radius, y radius, and this one, z radius. Right? And this is cylinder. So then this okay, so this should be something that looks like this one. Okay. So this is 3, this is 3. Here is 3 square root of 2. Okay, so it's ellipsoid. And the cylinder is, that's easy. That's it. Okay, so the thing is, solid bounded by surface here. So if we put them together, so what we have here, we have a ellipsoid, but the inside, we know the cylinder is inside now. cylinders now. There we go. This is radius 2, but this is radius 3. Okay, so what's the object? Well, the object is that here, this one here, not the inside. The inside is cylinder, so this one. So when you look for the there, 1, 2, 3. Okay. So this is the domain of integration. All right. There is 2, 3, 2, negative 3, 2, 3. Okay. So what's the function to integrate? The function to integrate is this one here. All right. So the this one now is the z 1 minus now. Okay. All right. Let's just write this down as because that's easier from here. Z equals this 18 minus 2x squared minus 2y squared. Yeah. Okay. So this one. So the function to integrate is this one. There. Okay. So this is our area. So we know integrations. Square root of 2x squared. Okay. So this is the area. All right, so let's change it to polar. You change to polar. So well, in polar, this is a rectangle. Why? This R is between 2 and 3, and theta from 0 to 2 pi. That's easy. Okay. So this equals to R theta from 0 to 2 pi. That's easy. Now the integrand is that's 18 minus R squared. Okay. And dA would be R, the theta. Now because we have this extra R here outside this square root, then this would be easy then. Okay, so let's compute that one. There's no dependence on 2 pi, sorry, on theta. So just multiply by the range of theta, which is 2 pi. Okay, and here's the integral is this is 1/2 the whatever UD R. Okay, so this becomes negative 1/2. Okay, and here because power 1/2, you integrate becomes power 3/2. And 1/3, 3/2, 2/3, which is okay. And you plug in R equals 2, R equals 3. Okay, so you get this is negative 2 pi over 3. This is 18 minus whatever there. Okay. All right, so that's one example for the this problem. Okay, any questions? All right, so then we are pretty much done with our material. And so we'll review all this material for the final exam tomorrow, and also the just more problem session that came out Thursday. All right, if there's no questions, then I will stop the record.